So 4-5 is all about real zeros of polynomials. And the idea here is, how do we find zeros if we don't know how to factor something? So we know that x-intercepts are really important for parabolas, for a lot of things. And x-intercepts are important for polynomials. And we are actually able to have ways to find where the zeros are without just simply factoring and without having to look at a graph, even though we're going to utilize that sometimes. So there's a couple theorems that we need to do first. You'll see synthetic division throughout all of this. I'm hoping you remember synthetic division. And here we go. So the remainder theorem deals with if you divide one polynomial by another, what the remainder is, kind of like in long division. So if you have a function f of x and you divide it by the factor x minus c, the remainder is f of c. So a quick example of this is, if you have f of x equals x cubed minus 2x squared plus 3x plus 4, and you divide that by x minus 1, how can you quickly tell what the remainder is without having to do long division, without having to do synthetic division? You were just going to do f of 1, the 0, I guess, of the factor in the bottom. So we would do 1 cubed minus 2 times 1 squared plus 3 times 1 plus 4, which is 6. Now, why does this matter to us? Because this leads us to the factor theorem. And the factor theorem says that x minus c is a factor of f of x if and only if f of c equals 0, aka the remainder is 0. This is a way for us to tell if something is a factor without having to know what the factored form is. So I can give you something like this. Is x minus 2 a factor of 4x cubed minus 5x squared plus 8? So if this thing were factorable and this were one of its factors, how could I tell? We could divide this by this, which basically leads us to plugging in 2. 8 times 4 is 32, 4 times 5 is 20, 12 plus 8 is 20. So the remainder is 20, so it's not a factor. It's not going to help us find x-intercepts, which is the whole goal of all of this. So let's get to what... Oh, you know what? There's one thing before we actually get to it. The last theorem we have to talk about is the possible rational roots. Fancy name is the rational roots theorem. If you have a polynomial in the general form, how can you tell just by looking at it what the possible nicer roots are? When I say nicer, I mean whole numbers or fractions that you can come up with. How can you tell just by looking at a polynomial? You take all the factors of the constant, and you're going to divide those by all the factors of the leading coefficient. So let's take a look at an example. If we had x to the 4th plus x cubed minus 13x squared minus 25x minus 12. If this thing has nice zeros, whole numbers or like fractions, like a half or 3/4 or 2/3, stuff like that, they are going to be the numbers in this list. We look at this number. What are the factors of 12? 1, 2, 3, 4, 6, and 12. We look at the leading coefficient. What are the factors of the leading coefficient? It's just 1. So we're going to take all of these numbers, divide by this number. So our possible numbers, where we would look, we need a plus or minus for all of them. But if I had to guess where x-intercepts were, these are the 12 numbers. 1 and -1, 2 and -2, 3 and -3, 4 and -4, -6 and 6, 12 and -12. Those are the numbers I would guess to see if they were factors. We could plug in these numbers into here. If you get out 0, you know we can factor it out. Let's do a problem where we're finding real zeros. So find real zeros of 2x to the 4th plus 11x cubed minus 5x squared minus 43x plus 35. If I were forcing you to do this whole thing by hand, you would start with a list of numbers that you might guess were possible zeros. We take all the factors of 35, 1, 5, 7, and 35. We take all the factors of 2, 1, and 2, and we would have this list 1 divided by 1, 1 divided by 2, 5 divided by 1, 5 divided by 2, 7 divided by 1, 7 divided by 2, 35 divided by 1, 35 divided by 2. So if I had nowhere else to begin, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I have 16 possible numbers that could be x-intercepts. Now, in class, when I give you questions like this, I'm going to give you one of two things. I give you a graph so that you can see where they are instead of having to guess and check through all of these. Or I would just simply tell you what some of the zeros would be. In this case, let's say that I give you the graph. So I wouldn't tell you that you had to graph this, but let me give you the graph. So I'd give you a picture and I'd say, use this graph to find some zeros, to factor this thing completely, to find all real zeros. So I could give you this picture. And it looks like it crosses nicely in a couple places. Like right here, it's probably a little hard to tell, but it doesn't hit a nice number. Here, though, looks like 1, 2, 3, 4. It looks like -5 is an x-intercept, is a 0. It also looks like 1 is as well. I can go to the table and check. 1 is also a 0. Not 5, -5 is. So with a graph or with me giving you information, I'm going to tell you that these two numbers are real zeros of this polynomial. We're going to factor them out so that we can find the rest. And what do I do when I say factor out? We're going to do synthetic division. So I'm going to take 1. Doesn't matter which one you start with. You'll end up in the same place regardless. But I'm going to take 1. How you do synthetic division, you take all of the coefficients from the polynomial. 2, 11, -5, -43, and 35. How this works, you always drop the first number. You multiply that number by whatever is over here. You put that over here, and then we add. 13 times 1 is 13, and we add 8. 8 times 1 is 8. We add, it's -35. -35 times 1 is -35. And this last number is always your remainder. And if it's 0, that means it's a factor. What do these numbers mean? If I were to stop here, we could tell that this polynomial right here, and you can tell I'm running out of space, could factor to, or does factor to, not could, but does, x minus 1 from this times constant x, x squared, x cubed. These are all the numbers in front of those things. 2x cubed plus 13x squared plus 8x minus 35. These two things are equal. We've started factoring without knowing exactly how to factor this thing, without having a method to do it. Now, I also told you that -5 was a factor. So we're going to take -5 and we're just going to synthetically divide it out of all this stuff that's left. We're going to drop down the first number. 2 times -5 is -10. We're going to add those two things. We get 3. 3 times -5 is -15. We're going to add those. That's -7. -7 times -5 is 35. And just like last time, our remainder is 0, which means it's a factor. What does this 2, 3, and -7 do? Constant. This is in front of the x. This is in front of the x squared. So right now we can further factor our original polynomial to x minus 1, x plus 5, and then 2x squared plus 3x minus 7. When we get down to a quadratic, even if it's not factorable, you are able to find a real zero because you know how to do the quadratic formula. There's no quote-unquote quadratic formula for a quartic. There's no way to plug in numbers to find our 4 solutions to when it equals 0. But if you can get it down to a quadratic, this either factors all the way so you can find all nice numbers, or we can do the quadratic formula for this, and this one actually requires the quadratic formula. Opposite of b, plus or minus the square root of b squared. 3 squared is 9, minus 4 times 2 times -7. 4 times 2 is 8 times -7 is -56, so it's going to be plus 56. All over 2 times a is 4. This is -3 plus or minus the square root of 65 over 4, which doesn't simplify any nicer. So the answer to our problem, find all the real zeros of this polynomial. Well, 1 is one of them, -5 is one of them, and then there's 2 more. And we're going to write it as one whole thing. -3 plus the square root of 65 over 4, and -3 minus the square root of 65 over 4. If we were to plug in these 4 numbers in for x, you would get 0 out from the polynomial. All right, let's do one more. So what if I asked you to find all real zeros of f of x equals 2x cubed plus 3x squared minus 2x minus 3. Ooh, that's not focusing. There we go. So again, if you don't know how to factor something, I have to give you a graph or I have to tell you an answer so that you can start the problem without it taking forever. If you had to just start with nothing else, you could start with our possible rational roots. Factors of 3 are 1 and 3. The factors of 2 are 1 and 2. So our list is 1 divided by 1, 1 divided by 2, 3 divided by 1, 3 divided by 2. This list is not very long. There are only 8 numbers. So if I honestly asked you to guess and check till you figured out which plugging in one of these will equal 0, that's actually not too bad. But let's do this problem this way. I'm going to just tell you, instead of looking at a graph, I'm going to tell you that -1 is a root. So what do I do? So if I give you this, you're going to take this number and you're going to synthetically divide it out. And we could rewrite this factored thing as x plus 1 times 2x squared plus 1x minus 3. This thing actually factors, I believe. X plus 1, 2x. This is plus 3 and minus 1. 2x squared minus 2x plus 3x, yeah, minus 3. So this thing factors all the way. So we can have our answers of our zeros, our -1, -3 halves, and 1. But the other thing is, we can actually factor something like this. When I give you cubics, you should always, always, always check if we can factor by grouping. This is a method that you do know how to do, or you've been taught before at least. So this is a problem where I actually wouldn't have had to have given you anything because I could have told you it's factorable, please factor it. But the idea here is you're just trying to find all the zeros of these functions, all the numbers we plug in to make the zero, because they're important and they're helpful. When we get together next, we'll talk about how to find complex zeros, ones that have i's and stuff in them, and that takes a little bit longer.